In the last lecture, I described um, what is called the classification problem in machine learning, and then constructed a test to understand the behavior of quantum evolution under a chaotic map. But this machine learning situation is much more widespread, and these days there are not only courses which are taught on the subject, but also degrees which are offered on the subject. So there is a huge amount of material. I will only give a brief summary again, just to give you some familiarity with all the terminology, but going much more beyond than that is outside my scope, and also I don't know that many details about all these techniques myself. So just give a quick summary. So the problem is to identify boundary between classes of different properties. So it's a binary problem. Some objects have one property, some objects have another property. All you are interested in is find the separating boundary between the two classes, and in general the boundary can have a nonlinear structure. So to get around that, there is this construction of a feature map which takes some set of properties. I labels the various data points and embeds it into higher dimension. So x is some dimension, phi of x is a larger dimensional space. And the purpose of doing this is what is a nonlinear boundary for x becomes a linear boundary for phi. And then the problem is much easier to tackle. It's exercise in linear algebra, for which lots of well-known methods are available. The penalty you pay is you are now searching in the larger dimensional space. So there are so-called parameters defining the number of points in a set of dimensions. So those are the parameters you need to search to figure out boundary in the space of whatever dimension, and in any dimension, even for a binary problem, you need at least 2 points. You can have more, but 1 point will not define a dimension. 2 points, you can say that, okay, there is some variation along some particular directions. So if you are going into higher dimensional space, the parameters to search will become 2 to the power the dimensionality. you need to look at those many set of points. In every dimension, there will be at least 2 points, if not more. And you have to characterize the values of all of them, and this is where the penalty comes in. You made the problem linear in a higher dimension, so this is space which you need to search. Well, if the space becomes too large, then your effort goes up. And there is a penalty which has a problem which also has been given a name. It's called barren plateau, and the word plateau means that the function, whatever you are looking at, is varying very slowly in that particular direction. And so minimizing in that is not easy. So the gradients come out to be very small. How accurately you can estimate them is another story. And algorithms basically get stuck if the dimension is too large. So you want to keep this small, but still get a linear problem, and that is where all the techniques go in. How do you find a suitable feature map? And there are ways of doing it in the classical computational paradigm, and what I illustrated last time, that in the quantum case, you can replace this feature map by a density matrix. But again, the question of dimensionality remains. If the dimensionality becomes too large, you will end up with various kind of complications in the sense of how do you minimize the directions where the gradient is very small. Okay. So this is one part of the story, but people still play with various tricks how to simplify this as much as possible, and for that there is something called representation theorem, which says that this linear classification is sort of guaranteed. Once you found a good feature map. And so what it says that you can always find some vector W. This phi is also a vector in some higher dimensional space, which is a linear combination of this phi over various data points, and I now is not the set of the full data sets, but I belongs to only the points on the boundary, which is a much smaller set. So there is an advantage that only boundary points are important. The region which is called bulk, which is the interior of the set, it can be safely ignored, and the points which appear over here, the ones on the boundary, they have been given a name, which is something you will find referred to quite often. They are called support vectors. And finding alpha I is a task for linear algebra algorithms which are labeled as support vector machines. Okay. So, you do not need the full description. Boundary is much smaller than the part in the bulk, but once you find this, then the problem of classification is solved in a kind of straightforward manner. So, the class label is taken as a sign. There are only two classes, you can call them plus or minus on either side, and after that it is a dot product. And this can be interpreted that this W is a normal remember it is defined by only the points on the boundary, and you can interpret it as the what you call set of values on one side and the other side. They differ by the separation between the two, and this one is offset. Yeah, so this is the same W, which I could write it with the same symbol. So, this is what the support vector machines do. You find the set of boundary points, they define a hyperplane, and the distance between two classes is the distance between hyperplane of one support vectors, hyperplane of another support vectors, which is measured in orthogonal direction, which is normal, and then you can put an offset depending on where the 0 of the structure is, and then the label is basically just a sign one side or the other. So, this is all the machinery of this linear classification problem is, and all the cleverness is now gone into how do you find this alpha I, because they define basically the hyperplane which separates the two classes. So, there the so called kernel trick comes in, which evaluates only the relative placement of the 2 points, and in some sense it is again a dot product. And the point is that it can be evaluated without explicit calculation of the feature map itself. It just gives relative position. It just defined as a separation between these two vectors. We need it actually only for the so-called support vectors. We don't need it all over the place. But the point is that it can be evaluated without reference or without any detailed evaluation of finding the map. So that makes it a little bit easy, and the life is even simplified further, that what even k, whatever ij, need not be evaluated accurately because only class label is predicted from the algorithm. You are not interested in calculating this also to high accuracy, because ultimately we are going to do something and look at only the sign, and as long as the sign comes out right, the magnitude may not be quite accurate, you accept the job, and that also helps in the estimate of how much computer power you need, and that is essentially the story. Yeah, one thing I should mention, that alpha I is obtained by fitting the support vector machine to what is called training data. You have some data set where you already know the labels, and that you use to train this algorithm, and once you have found these parameters, you can give it a new data point and then ask us to predict. And this is where a lot of uncertainty goes into the model. How good a sample of training data have you produced? And if it is not what you call enough variety, then the machine is not going to do a good job. Okay. So this is all that you need to know to understand how this classification problem is constructed, and this exercise of support vector machine is more involved. It basically you are fitting to the training data some unknown parameters, and how do you determine it is a exercise which takes many forms. There are so-called Lagrange multipliers, unknown coefficients, which you put in a function, which are determined. Then there is a so-called primal version, dual version of the function, which you optimize, etc. So those kind of details I'm not going to go into, but they all are part of the language if you really want to understand how this support vector machine works. Okay. There is a related problem which I can point out, and many times both of them are treated in the framework, which is essentially the same thing. The language is little bit inverted, and that problem is called regression, and it is the job is to minimize deviation from fitting function. This is something which all of us have tried in some form or the other in analyzing some experimental data. Some set of points are there, you want to find a good curve which goes through all of them. Okay, it's a kind of a contrast to this classification problem, which says this is formulated as maximize the margin and the margin is the distance between the two hyperplanes which form these support vectors. This is a separation on and they are related because one is maximization, the other is minimization. You are measuring some distances, and you can rewrite one versus the other. But these are all various techniques, and we have tried regression methods many times in fitting some laboratory data by just minimizing this Cartesian distance. This is just the difference between the fitting curve and the point, square of it, which measure the distance, summed over all the points, you minimize it. So you can define a distance in some manner. Cartesian distance works most of the time, but you can have different choices if you want. So this is as much as I want to describe in case of this classification problem. Yeah.
Number of parameters to search greater than or equal to 2 to power dimension. This dimension is higher dimension or the original dimension?
This the higher dimension. And in whatever the data points you have at that particular dimension.
Number of parameters has to be larger than.
Yeah, at least in every dimension you need at least 2 points. You can't have less than 2 points because then it will not define a coordinate, whatever it is. Yeah. Okay, so now I want to define a generalization of this. Incidentally, this falls in a machine learning, both of this regression and the classification problem, which has been called supervised learning. That is because it uses what I call a training data. You feed it some known results, then you parameterize various functions based on those known results, and then use that parameterized function to make some new predictions. There are other versions of machine learning, and they are based on what are called neural networks. The reason for that nomenclature is the same, that we want to follow the same strategy which is somehow built inside our brains. Okay, we don't know exactly what it is, but some amount of information is available from, well, basically cutting up brains and looking what is inside kind of thing. You get some structural information, though not much about the dynamics. Okay. So, I mean, one lesson which was important over here, that you only look at boundary, you do not look at the bulk. That is the feature which is there in the way we observe various objects, and it has been built inside this, but this is more general. So, what is known as the brains have highly connected neurons, and they are often arranged in various kind of layers. So, the information goes in a sequence from one layer to the next layer to the next layer, and somehow there is a what you call reduction towards whatever feature you want to look at as it progresses. How exactly it works, we don't know, but that is a broad understanding. So, how do you mimic this structure, and again the computer models are very simple, and they just look at neurons as a some object which is in a binary state. The biological terminology that the neuron is either quiet or it is firing, doesn't do much else. So, well, you have two states, and depending on whether it is quiet or firing, it does a certain job. It collects the signals from its neighbors, and then it decides whether to remain quiet or whether to fire. So, it is like this binary process depending on some sign function. What goes inside is a collection of the input from its neighbors. So, this is the either quiet or firing depending on its so that brings down the whole machinery to a binary problem. You have a two-state system, and you connect it in many different ways, which defines who is neighbor to whom, etc. And there is a kind of generic model which has been around in physics for a long time. And it is defined by the Hamiltonian, where you have binary variable typically labeled at Ising spin plus or minus 1. There has been some influence from the neighbors, which is denoted by this coupling SI/SJ, and this sum is over who is neighbor of who, which depends on the structure of the geometry. So, the sum is over I and j, which are all neighbors, and I alpha ij is the strength of that particular connection. And this one is like a background field. In case of spins, you can call it a magnetic field. For every spin, there is a background field, and if you take this Hamiltonians and try to construct the dynamical equation for each spin, you will find that its value will depend on the sum over its neighbors and plus some constant, which in essence is very similar to what goes on over here. Some neighbors were involved. Either they were the boundary points, here they are the physical connections in the network, and then there is some offset. So, this model has been around for many years, and well, studied quite a lot. Now, you don't want to make it arbitrarily complicated by putting too many connections in this alpha ij, because the more connections you put, it becomes higher and higher in terms of the computational complexity. So you keep this number to some reasonable value and see whether it can generate certain dynamical features. So there are what I call restricted models which in some sense include this layered structure. So what it does is there are a set of spins in one layer and then another layer and third layer, etc. What the restrictions means that a point or a neuron in one layer is connected only to neighbors in the next layer. The restrictions means that there is no connection within the layer. Okay. And then you have something here, etc. And you can continue the game. So you send in some signal from here, it gets mixed up according to all these interlayer couplings in some way, and after processing, some result will come out which you interpret as output. Okay. So here is some output. And by playing around with these kind of systems in many examples, people discovered that these restricted models do as good a job as so-called unrestricted model with lots of couplings. So of course, it is a simpler structure. So this is what is used in practice. So this scenario, again, now you want to use in a what you call a predictive exercise. So you have to find what these parameters of alpha and beta are in some particular problem. Okay. Every problem you have to tune the parameters till you get the answers which are good enough, and this setting is actually used for what is another label. It's called reinforcement learning, that you have these parameters, you are going to tune them or vary them in some particular manner, and if the change is such that your prediction becomes better, you give a reward in the sense that, okay, tell the whatever program that this particular value or this particular change is good. Okay, so you have to train using some method or the other every one of these problems, and that training in some sense is external. You can't get something out of nothing. You have to put an external input. In the actual biological systems, that external input comes from the environment. Okay. The what you call machinery of either brain or genes can't decide everything for themselves. The external agency comes and tells this is good and that is bad, and so something is selected. And that selection is an important part of the process, and that is the place where all the machine learning and artificial algorithms struggle. Who is going to do the selection? If you don't give it the right data, it will give you nonsense. And well, these days it is all over the place, ChatGPT or whatever else versions of it. If you have not trained it properly, then the kind of answers it produces are either nonsense or sometimes even damaging. So then you have to shut down that this is not doing the right thing. And this reinforcement learning is actually some sort of selection, that yes, you made this change and you moved in the correct direction, so you keep it. So and this is the story in all these models which are trying to mimic biology. I don't know whether you have encountered what are called genetic models. They were in some sense earlier versions of this kind of logic. You have some data and some parameters, and then you change the parameters which are called mutations, and then you keep the mutations which are helpful in a certain sense, and ultimately you converge to some particular answers. So those genetic models were there maybe some 20 years back. People were playing with it. Now it has all been superseded by this machine learning version, where it is more powerful. But the philosophy remains essentially the same, that you are changing parameters and some external input will tell you what is going in the right direction and what is going in the wrong direction. So this is and in this particular context, I want to give another illustration of yet another type of machine learning exercise, which has been called unsupervised machine learning. Okay. And the only reason for addressing that is, again, this can be made much more quantitative rather than looking at some only qualitative ideas. So what does unsupervised machine learning do is you don't have precise training data uh, given to you, but you still want to train your model and make some prediction. So it uses what are called analogies or similarities. Instead of explicit training data. So some data is given and it has its own collection of past history, and it kind of looks around. So it looks like this. So let me try working in that particular model. May succeed, it may not succeed. If it doesn't work, we'll try something else. But you have to use lots of analogies, and after that, it's a generalization. And this is more advertised now as artificial intelligence compared to machine learning. But it's only a little bit of a change in the terminology. The ideas are all similar. Yeah. Yeah, reinforcement learning does use training data, because you have to tell us whatever is the correct, and then it will go in that particular direction. Yeah, so whatever training data is tells you, it allows you to judge the reinforcement. That's, without that you cannot tell. That is, how do you reinforce? Because you have to know that it is going in the right direction. It's not very different than giving a chocolate to a kid when he did a good job. Okay. Well, this is a reward. So then behavior will be modified. That kind of whatever technique will be reinforced. Okay, so now let me quantify this. You still have to use analogies. What kind of analogies you are capable of encountering in a practical situation. So, assumption that the practical it's a distribution of whole set of data. You assume that underlying it is some physical process which produced it. And then comes the input from physics, that yes, you have encountered various kind of distributions in lots of physical phenomena. What is a generic structure that describes it? and that goes under the name of Boltzmann machine, which essentially says that what is the distribution is given by the well-known Boltzmann's factor in statistical physics. This z is just a normalization partition function, but the distribution is given by exponential of some temperature, inverse temperature, times some Hamiltonian. And this is a consequence of the assumption that what produced the distribution where there was some physical process. And that now gives a particular constraint that it is not an arbitrary distribution, it is governed by some Hamiltonian under some parameters. The Hamiltonian can all be same kind of thing, whatever you want to put in. Many times it is again reverts to this what you call the spin glass model, some spins, some connectivity, and some background field. But we don't have to go that far. You can actually deal with it in a more general fashion. And what you want to do is this H can be estimated, then any other observable can be evaluated by the usual formula that this is the weight, the probability weight it becomes, and any quantity you want to calculate, it's a sum function of the states, and you just calculate a weighted average. So the job of this unsupervised machine learning is this: somehow figure out what the distribution is, and then you can make all kind of predictions for any observable. It doesn't matter, the observable is not used directly in calculating the H, but H is obtained by some fit to the data, and that can be estimated by, again, a variational method where you change various parameters till you minimize some target function, and that will tell you that you have a good estimate. So here the target function is known as well, it's not, it's a minimize. A quantity called relative entropy. This is again, well, you are doing statistical mechanics, you have put Boltzmann's distribution, you can define entropy. It's not a big change for it. So this is, you can call this thing as a probability of some state. and from that you can calculate all kind of entropies depending on it. And what you want to minimize to get a good estimate of this distribution is the relative entropy, the computer scientists happily refer to it as KL divergence. These are the name of the two people, Kullback and Leibler, but it's most of the time just referred to as a KL divergence. Names are too complicated to repeat all the time. So, what is this particular function? And it's denoted by this particular symbol. The two vertical bars define a relative structure. P is one distribution, Q is another distribution. And the definition is that it is the relative entropy is defined as this particular difference. Okay. By construction, this function is asymmetric between P and Q. You interchange P and Q, you will get a value which is something different. It's not the same thing, but still it is a very useful function for a very simple reason that it obeys some nice properties, and it can be written as a difference of what is called the sum is over all the states, and all probabilities will all depend on the states. So, in terms of entropy, this can be written by combining this either way. Sometimes it's written just like that, doesn't matter, this kind of trivial thing, but the nice property follows from the simple identity that this function log, it is always below the tangent line at x equal to 1. So, if you plot the log, it has feature like this, and this line which is x minus 1 is nothing but the tangent at that particular point, and the two have a nice behavior that they will be equal only if x is equal to 1. At any other point there is an inequality. And so, now you can rewrite this thing as this computer scientists write this as log as a base 2. So, there is a factor of log 2 somewhere if I want to convert this to that, but I don't okay, logarithm to the base 2 will be larger than this ln. So, there will be some 1 over log 2. Okay. doesn't matter, it's a proportionality constant which is not important. But what is important is how this simplifies. So, I will have p times 1 minus q over p, and this quantity will be larger because I am using this inequality uh, in the opposite sense, that it's a reciprocal. Instead of log x, I am using is 1 minus x, whatever it is. But this is what it becomes. Yeah, because I have changed the sign here, it was less than or equal to, but there is a negative function, so it's a greater than this function, not a big problem. And the important point is that now this sum over states is trivial, because the first term will be just sum over all p's, which is 1. The second term will be sum over all the q's, which is also 1. So, 1 minus 1 is 0, and that is a nice property of this relative entropy, that it is always positive. And on top of that, when it will be 0? When x is equal to 1. That means p and q are equal. So, when the two distributions coincide, relative entropy is 0. If they do not coincide, it is positive. And that gives this strict method to find the distribution. I calculate relative entropy and I minimize it. Okay. So, S, P, Q, so now the job is straightforward. I have one distribution parameterized by some values of couplings, whatever I put in. I have another distribution. One of them might be coming from the data, the other one is the fitting function, and I change all the values so as to make this quantity as small as possible. And if I succeed, then I have found a good model to describe data, then I can calculate all observables, whatever I want, no problem. Okay. So, this is a strategy of unsupervised machine learning. Okay. Now, the whole structure is written in a language where I can easily generalize this to the quantum situation. And that tells you, well, if you replace this all parameterization of data from the classical case to quantum case, will I get any difference? Or more than that, where will the difference be? So, what do we do in quantum theory to calculate the same kind of thing, some distribution, some expectation values, which are all well known functions. So, this probability of some state is replaced by the density matrix. And if I want to calculate this O, which is some over say some x, well, x is a label for the state, will be a linear function of the density matrix. All I need to know is the values of O for every component, and then whatever I was doing over there, I have a direct connection. And this Boltzmann function also has a place because the density matrix is known to be positive semi-definite. So, if you want you can write it as an exponential of some Hamiltonian because it's a positive semi-definite matrix. That's all you need. All these eigenvalues of whatever this is, they all have to be positive. That's allowed. And more than that, this S of rho and sigma, the relative entropy, now defined not from these distributions, but from the two density matrices. It can be given the analogous definition, trace of rho, rho log sigma, and it can be easily shown that it obeys the same properties, that it is positive or and it will be 0 only when the two distributions coincide. So, the arguments which allowed you to produce all these things go through. All you need to do is jump from the probability distribution to the density matrix. Where is the difference? The difference is that in quantum theory, the two operators may not commute. The density matrix and the observable. So, or rather, you can write a very simple statement that when they do, they can be simultaneously diagonalized and the problem becomes classical. Because if I have a situation where both of them can be simultaneously diagonalized, then this is a product of two diagonal matrices. I go to the basis, trace is invariant under any of these jugglery, and the product of two diagonal matrices just gives me this. So if these two commute, then I'm not going to get anything more than what is available in the classical formalism. Difference will come when they don't commute. And that means that the advantage or whatever difference produced by quantum theory will be available only in particular situations. You have a distribution given by rho, but if the operator that you are trying to measure has some relative property compared to rho, then in some case you might get some advantage, in some cases you may not get any advantage. So it's a relative and now you can ask a very explicit question that I want to get maximum quantum effect out of this problem as much as possible. And that can be phrased as I will maximize the norm of this particular commutator. If the commutator is 0, there is nothing to gain. See, I am talking only about whether there is going to be anything extra in the quantum advantage, not how much advantage is there in the classical machinery. Of course, it has its own formulation and its own ways of finding solutions. There will be advantages inside there, the classical ones, but this is a relative question, is that am I going to get anything more in the quantum theory? And this maximum advantage when the commutator has the largest norm. And yeah, there are various connections to this behavior which I don't have time to go into, but they are worth learning anyway. They are powerful results of these statistical distributions and their accuracy. I will mention them because knowing them will be useful, and for those who want to work on it, they should really go through those derivations. So one is a quantity called Fisher information, which is actually the same problem as fitting a data to some particular distribution, how good a match you are making. And this Fisher information is the quadratic approximation it remains true in quantum case also. You can define a quantum feature information. I am not going this far. First, you have to learn this. Uh, so this I demonstrated that this function is a minimum value when the two distributions coincide. What is this behavior in the neighborhood of that minimum? Of course, it will be a quadratic function for any smooth changes of parameters. And if you find that quadratic function, what it is called Fisher information. And together with the Fisher information, there is something called Cramer-Rao bound. It is a lower bound on accuracy which is this lower bound on accuracy is in the same sense as the uncertainty principle, trying to determine some variable as accurately as you can, and there is a lower limit. You cannot go all the way till 0. And this is these are both well-known results in distribution. And it's essentially reciprocal of Fisher information. Fisher information is the quadratic around the minimum. If the minimum is flat, very broad, then there is a large uncertainty. Well, yeah, by Fisher information, I mean the coefficient in front of that quadratic functional form, the proportionality constant in the quadratic case. So if the distribution is rather broad, the uncertainty is large, and the distribution is quite sharp in terms of that parabola, while the uncertainty is small. And both are very important result in all the statistical analysis. And given all these properties of whatever happens in quantum cases, both these things go through. And there is a quantum Fisher information and there is a quantum Cramer-Rao bound, which tell you how accurately you can determine various quantities. And they are important for that particular reason. So now let me go back and ask whether I can really solve the problem. And this commutator. And if you go through all the exercises, it does turn out that the expressions for the quantum Fisher information and quantum Cramer-Rao bound turn into this particular norm. This commutator of rho and O will explicitly appear, that this will determine the bound on the accuracy directly. How does then one look at this kind of object? The applications go in two different kind of settings or two different formulations, and that I can rephrase by rewriting this expression for this rho and O. So this trace of rho and O can be written as a more general feature where I have found a diagonal form. Both of these are Hermitian objects, so they can be diagonalized by unitary transformation. So I can write down the rho, the diagonal form for it. What is the operator? Again, the diagonal form for it, and this U and U dagger represent the relative unitary transformation between the two. And then I can ask it in two different ways. That suppose I take O as a given object, I will write it in the diagonal basis. And then what is the best rho to I choose an operator, then I say I want to get the best density matrix, which I can prepare the state and measure it. What is the best density matrix I can do? And that is one way of writing. And I can also say that suppose I am given a state, and what is the O that is most sensitive so density initial state of the density matrix is given, and I want to look at the operator which is most sensitive given this particular state. I can ask either of the question. In one case, it will be the focus on the operator. Other case, it will be the focus on the density matrix. It doesn't really matter. But in both cases, or well, depending on what you want to do, that the relation between the observable and the rho comes out, and one of the uses for this analysis is actually high precision sensing. So I want to measure some particular property. What state should I prepare the instrument in? Not all things are going to give you good control over the quantum feature. So some states prepare apparatus for and this is when it's going in a different direction compared to whatever the unsupervised learning is, but it's a practical application. You can ask these kind of questions. And for that, now so that I also said that the quantum Fisher information and this Cramer-Rao bound they depend on this particular quantity. So the final job is to maximize this object, and that I could work out. It turned out to be a simple exercise because the maximization could be done. So you do not have to iterate parameters and minimize this divergence, etc., etc. It was finished in one step. And all the non-commutativity property um, turned out to be very important inside this. What is also quite clear that you can literally handle this particular object because density matrix is bounded. Its eigenvalues are positive and between 0 and 1, and you can fix whatever normalization you want for the operator. It's always arbitrary because it's a linear function. You can scale it up, you can put whatever norm, and so it is literally possible to maximize this. I can put norm o equal to 1, this is less than or equal to 1, and I find the relative orientation between the two, which does the job. So simplest case is 1 qubit. So let O be some observable, doesn't matter. In 1 qubit you don't have too many directions, I am making it proportional to sigma z. Okay. Then which are the combination that will produce largest non-commutator? The answer is very straightforward. You know that a generic density matrix is given by this. Want to maximize the commutator, and implies this is it has to be some combination of x and y. It doesn't matter, there will be some constants which will be taken care of by the norm, whether it is sigma x or sigma y, some combination doesn't matter. But there is a much more to this fact that it's not only R is in the equatorial plane, the largest value you will get will be when the magnitude of R is equal to 1. Okay. That happens to be a pure state. So you want maximum sensitivity, you are better off using a pure state. If you use a mixed state, yes, you can get some value, but it may not be as good as what you can get from pure state. And the other thing, I will have to go back to the network. So let me finish this argument. So let me go from 1 qubit to n dimensional density matrix. That also has a straightforward answer, which is obtained by saying that only terms which contribute to the commutator is actually the traceless part. It can have something proportional to identity, but that doesn't contribute to the commutator at all. So now I can ask again the same question. Let me take O to be some diagonal matrix, like whatever I choose over here, and try to find the object which gives the largest parts, and there is a way to do this. So traceless diagonal these are Hermitian as well. No, they are positive actually, doesn't matter. Hermitian is good enough. This goes into some bit of a group theory language which describes diagonal generators of a unitary group. They are written in terms of Hermitian matrices, and for n-dimensional group there are n minus 1 of them. You can write them in various ways. Doesn't matter, you can write it as linearly independent ones, etc. One of them, and the trace has to be 0, so you can put 1 in one place and minus 1 anywhere else, and that will give a linearly independent set. And there will be n minus 1. The one which is missing is the identity. It is orthogonal to all of them. and but these are not mutually orthogonal, so sometimes people use a slightly different basis which is orthogonal, mutually orthogonal in this case also, which goes like this, that you write a bunch of ones and then minus the sum of everything else. It's a linear combination of, if you want to write this, you can combine it with this some way. But the point is that there will be n minus 1 of these kind of traceless objects. And the question is, you want to maximize the norm. So which is the largest objects which you can construct, which is some linear combination of this, but maximum in magnitude. And that has a solution. You think a little bit, but comes out to be reasonably simple, that I write down a generic matrix which is traceless. Okay. So I can arrange it in two parts. Some terms which are positive, some terms which are negative, and the total trace is 0. So what is the largest magnitude I can construct from this kind of terms, which is a linear combination of the generators. Okay. And I take all the positive term and add them up together and put it in one place, take all the negative term and put it in some other place. And then all the job of the other generators will be to subtract off from this minus 1 some smaller terms. So that solves this problem, that how do I get the largest norm? I take this particular generator, it is not unique, there is it's a degenerate choice because where I put it doesn't get fixed by this, but it's a specific answer. Put all the positive terms in one place, put all the negative terms in another place, and then it reduces to structure like this, sigma z, for which I already know the answer. What is the corresponding matrix I should choose? That one of them will be taken as sigma z, the corresponding matrix will be the equivalent in the equatorial plane, the other one. For these two terms, I put sigma x and sigma y, and that will give the maximum sensitivity. So this incidentally gives a clean answer of what you call minimizing this relative contribution of the quantum term, how much extra you are going to get, or rather equivalently what is the direction of the most sensitive observation. It's explicitly given that given a particular operator, I can choose a density matrix setting to get the highest sensitivity and determining its accuracy. And I don't have to go through the whole exercise of minimizing this relative entropy. So the answer is simple because of all the linear algebra implicit in the structure of the density matrix itself. And that's a good result, and I worked it out. I have not yet written it in any paper or anything like that, but it is something which should be useful, and well, something probably more can be done about it. So I will stop here at this particular stage. Maybe if you are interested in next time, I can give this some explanation of these statistical language, Fisher information, and Cramer-Rao bound, and emphasize this particular point because it fixes everything. It will give you a specific eigen direction in which you should prepare the instrument to get the highest accuracy of the observation. And so once you know that, you can design your apparatus suitably that will do a good job. So it's a practically interesting result. All? Because the trace part is an identity matrix. Identity matrix will give 0 to the commutator. Yeah, so I can always write any density matrix as an identity plus something which is traceless. Yeah, it can always be written. I mean, this is a true in arbitrary dimension. Trace of rho is 1, this determines the coefficient of identity, and everything else is traceless. Because it is whatever this traceless part is, it is still a Hermitian. So I can go back to this kind of situation. I will determine the diagonal part, the best in terms of magnitude, and then afterwards decide the rotation to get the maximum commutator. So what I have done is maximize the magnitude of the diagonal part by choosing specific values, and then the relative orientation is decided the same way, that if one of them is sigma z, other one I should put in the equatorial plane of that particular sigma z. So I mean, this is still true that yes, the maximum value will be obtained when magnitude of this is largest, magnitude of that is largest, and then the rotation is also the largest. It's all coupled together, but it can be written like that because of the simple algebraic structure.
Could you clarify what the sensing protocol is? Like, you said that there is some observable that we want to measure, and we want to prepare a state that gives us the highest accuracy for measuring that observable.
Yeah.
So I'm trying to understand this in the actual setting. Let's say where I have some state and we prepare a probe, and the probe is such that it entangles with the system, and then the probe is measured. So how is this different?
It's the same thing as you know,
Like in sensing, usually I want to see the property of some state, right? And to interact with it.
yes, but what you are interested in measuring the quantum nature of the signal. Of course, there will be a classical signal also, and the classical signal will behave differently. What I am interested in maximizing the quantum part of the signal, which is dependent on this commutator. So if this thing is 0, I will get a classical signal, no doubt about it. But that is not what I am interested in. I am interested in what part of the quantum signal is present and how best to extract it.
So for more clarification, as you mentioned, that race is invariant under the ordering, right? For the observable, expectation of the observable. So where is it that a commutator shows this in the analysis? That makes it non-trivial.
Hmm?
Yeah, where is it that non-commutability shows
Yeah.
up? That makes it non-trivial.
No, the fact is that if they commute, then this description will reduce to this. So that means that I am not going to get any new quantum effect out of that particular analysis. I will get the classical part, no doubt about it. But if I am interested in extra quantum effect, what is new that I can say about the system, then I have to look at the situation when these two don't commute. Otherwise, I will get observation, they will all be fine, there will be some values, whatever it is, but they will be classical uh, observables or classical properties.
So I wanted to ask a different question. Can we reframe this analysis as a state preparation protocol? Like let's say I've given some state sigma, whatever that is, and via this Boltzmann machine formalism, I want to learn the representation for sigma.
You can do that, yeah.
And if
But what is, in general, it is much called quite broad. What I am only looking at is there any quantum part in that description which I can separate? And that I can do provided I look at only this commutator contribution. There will be other contributions. You can also ask a question of what is the best design for measuring that, and that is the part which will have its own structure and which I have not gone into. It can be applied. Yeah. The questions of tomography and what are the suitable observables, etc.